We now turn our attention to the multivariate chain rules for differentiation. We begin with the single independent variable one. Suppose that x equals g of t and y equals h of t are both differentiable functions of t, and z equals f of xy is a differentiable function of x and y. And then z equals f of x of t comma y of t is a differentiable function of t, and dz dt is equal to partial z partial x times dx dt plus partial z partial y times dy dt. Now this is the only chain rule that I'm actually going to prove, and it is a pretty long one. Suppose that f is differentiable at the point p equals x naught y naught, where x naught is g of t naught and y naught is h of t naught for some fixed value t naught. What we need to do is we have to show that z equals f of x of t y of t is differentiable at t equals t naught. Now, we know that z of t is equal to f of xy, which equals f of x naught y naught, plus f sub x of x naught y naught times x minus x naught, plus f sub y times x naught y naught, of x naught y naught, times y minus y naught, plus e of xy, where the limit as xy approaches 0, 0, e over the square root x minus x naught squared plus y minus y naught squared is equal to 0. This is from the definition of differentiability. If we subtract z naught equals z of t naught equals f of x naught y naught from both sides, then this is what we'll get. We'll get z of t minus z of t naught is equal to f sub x of x t naught y of t naught times x of t minus x of t naught plus f sub y x of t naught y of t naught times y of t minus y of t naught plus e of x of t y of t. Right, so this here, this piece right here dropped out, right, because we subtracted it out. Now if we divide both sides by t minus t naught, then this term will just come over t minus t naught, this will become over t minus t naught, this will be over t minus t naught, and obviously so will this. Now take the limit as t approaches t naught. So using limit laws, we're going to have this partial derivative times limit, this partial derivative times this limit, and then just this limit. Now, this limit here is dz dt. This limit here is dx dt. This limit here is dy dt. So now what we have to do is we have to examine this limit. So we can multiply this limit by 1, i.e. we're going to multiply by the square root of x minus x naught squared plus y minus y naught squared in both numerator and denominator. So we can write this. Now we can split this into two limits. Now as t approaches t naught, y will approach x naught, y naught. So the previous limit can be written as this. By hypothesis, this first limit here is 0. So all we need to do is show that this second limit exists and is finite. So we examine this limit. Well, first let's bring this t minus t naught into the square root by squaring it. Then we can write this as two fractions. And then we can pull out the square root and write this as a sum of limits. So this is what we're going to wind up with. Oh, I'm sorry, and also pull out that square. Now, both x and y are differentiable functions of t, so both of these limits are guaranteed to exist and be finite. Hence, the whole thing is finite. That is all we needed to show, which means that the original function is differentiable. And we've also now shown what it equals, and so the proof is complete. Now let's look at chain rule for two independent variables. So this says that if x is g of uv and y equals h of uv are both differentiable functions of u and v, and z equals f of xy is a differentiable function of x and y, then z equals f of g of uv, comma, h of uv is a differentiable function of both u and v, and we'll have partial z partial u is partial z partial x times partial x partial u plus partial z partial y times partial y partial u, and partial z partial v would be partial z partial x times partial x partial v plus partial z partial y times partial y partial v. This follows almost directly from the single variate case. More generally, if we have a function that is differentiable of m independent variables, call them x1 through xm, and for each subscript I, which is of course going to be a number between 1 and m, let x sub I be a differentiable function of n independent variables, call them t1 through tn. Then partial w partial t sub j, right? So w would then be a differentiable function of each of these n variables, and we would have, for some index j, or particularly for every index j, partial w partial t sub j would be partial w partial x sub 1 times partial x sub 1 over partial t sub j plus so on and so forth, partial w partial x sub m times partial x sub m over partial t sub j. Right, so just take the partial of the function with respect to its first variable, then multiply by the partial of that variable by with respect to whatever this t sub j happens to be. Now, in multivariate calculus, we almost never need to worry about the multivariate chain rules, and this is because we can just simply substitute the variable functions x1 through xm into the function f of x1 to xm, and then differentiate normally using the single variate chain rule from calculus 1. Right, so instead of doing, for instance, this, why don't we just replace x sub 1 with x of t sub 1, right? X sub 2, t sub 1, t blah, 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 right? And then we're just writing w as a function of t sub 1, t sub 2, up through t sub n. Right, so we rarely ever have to worry about these chain rules. However, they are very useful in derivations and quite useful for differentiating implicitly defined multivariate functions. So let's consider the relation f of xy equals 0. Y equals f of x is a differentiable function of x. We will examine how we can use the multivariate chain rule to find dy dx. So you should remember from calculus 1 the method that we used to do this. We're going to now introduce a much simpler way of doing this using partial derivatives. So consider the function w equals f of xy. By the chain rule, dw dx is f sub x of xy times dx plus f sub y of xy times dy dx. However, w is equal to 0, so the derivative of w must be 0. So f sub x of xy, right, because dx is just 1, plus f sub y of xy times dy dx must be 0. And so solving for dy dx, we get negative f sub x over f sub y. And a similar method can be used for functions of several variables that are defined implicitly. So in general, implicit differentiation, if the equation f of x1, x2, up through xm, and then w defines w implicitly as a differentiable function of the variables x1 through xm, then for each subscript I, partial w partial x sub I is negative f sub x sub I over f sub w. And we are going to look at now an implicit differentiation problem with this function, x squared e to the y minus yz e to the x is equal to 0. So it's already written equal to 0, so our function of xyz is x squared e to the y minus yz e to the x. And just for clarity, I'm going to put that equal 0 there. So let's just find all the partials. So f sub x would be 2x e to the y minus yz e to the x. F sub y would be x squared e to the y minus z e to the x. And finally, f sub z would equal negative y e to the x. So if we wanted partial z partial x, this is negative f sub x over f sub z. So we get negative 2x e to the y minus yz e to the x all over negative y e to the x. We can cancel out those negatives and be left with 2x e to the y minus yz e to the x all over y e to the x. And it's as simple as that. Right? Definitely a lot easier than the Calc 1 implicit. So let's look at partial z partial y now. Alright, so this will just simply be negative f sub y over f sub z. So we get negative x squared e to the y minus z e to the x all over negative y e to the x. And so we have negative x squared e to the y minus z e to the x. I'm sorry, get rid of that negative. All over y e to the x. And that's all that we needed chain rules for right now. We are going to use these chain rules in the future, which is why there is this video to introduce them, but we're never going to actually use them in a calculation type problem. And so that was multivariate chain rules.